Every day, coral reefs, home to thousands of marine species, are silently dying. Pollution, rising temperatures, human neglect. These vibrant ecosystems are turning to skeletons, and no one hears their cries. We are trying to help. Let us show you what we can do to start this recovery process. We can't let their colors fade forever. They can't speak for themselves, but you can.
We're Team Coral Conglomerate, and we're working on Project Ocean Life Control. Our sponsors, Biosphere 2, are working on groundbreaking research in their ocean environment. Their aim is to further develop resilient reefs to help win the fight against climate change and save coral communities around the world. In collaboration with Mo Marine Laboratories in Florida, their current focus is on Caribbean coral species due to the ongoing threat of environmental stresses. What is cool about this area is their massive 700,000 gallon tank that helps simulate real-world conditions. This gives staff the ability to test their approaches at a large scale without ever needing to leave the facility. Since our sponsors are in phase 2 of their plan, our project is focused on optimizing the lighting system to be automatic. I would like to point out that the natural light in this area is not optimal for coral growth, so we are filling in this gap by utilizing max-spec LED commercial floodlights to provide the necessary light intensity and color for coral, which will be hung on these trusses.
You may be wondering, what happens if they need to change the color's light or intensity? Well, first off, they have to cut off all electricity to every single light, get on a boat, row over, and individually change every single knob. Now this has a few concerns. As the power is off, they don't know what the color or intensity is of the light until they get back on mainland.
A faster and more efficient process, our team proposes to create a microcontroller-based system that allows researchers to precisely and wirelessly modify LED color and brightness levels in real time via a website and create and execute 24-hour lighting programs. Generate reports on system health and photosynthetically active radiation data, aka PAR data, that is collected from the system's connected quantum sensor. Our final prototype will incorporate 3 LED lights that the biosphere will fully expand to 86 LED lights.
So now I'm going to walk you through the electrical components of our system. To remove the manual aspect, we replace the potentiometers with digital potentiometers, or digipots for short. These achieve the same effects, except instead of having to manually turn knobs, user input into the website will control the resistance given to the blue and white LEDs. The Raspberry Pi Picos will directly communicate with the digipots, as Pi Picos are compact enough to fit inside the individual housing units and capable of executing these commands. The Pi Pico will receive these commands from the Raspberry Pi 5, acting as the main controller for all 86 max-spec LEDs and Picos, as the Pi 5 will be hosting the website. For a solid and secure form of communication between the Pi 5 and the Picos, every Pi will have a CAN hat attached to it, which will allow for communication via Control Area Network, or CAN for short. CAN allows for both communication and data transfer, which is crucial as PAR sensors will be scattered throughout the ocean environment. These PAR sensors will be attached to the nearest Pico, which will transfer PAR data back to the main Pi 5. Along with PAR readings, a temperature and humidity sensor will be attached to the Pi 5 and all the Pi Picos, which will allow the Biosphere team to keep track of the internal temperature and humidity levels within each housing unit.
At the heart of our system, the software is responsible for managing communication, controlling the lighting schedules, and ensuring real-time adjustments are made efficiently. Let's walk through how the software ties it all together. Each max-spec LED has a connected individual controller that can control light settings like color and intensity and access connected sensors. This individual controller utilizes multi-threading and asynchronicity to streamline process management and create an efficient mechanism for controlling the LEDs. Implemented in MicroPython, the individual controllers can modify and read microcontroller pin values to set light color and intensity and get data from the connected sensors. The central main controller can access each individual controller over CAN bus communication, providing precise and efficient control of each LED individually. Communication is facilitated through the ISO 15765 transport protocol to enable multi-frame sends among the network. The main controller also has access to the Biosphere 2 Ocean Sensor Database to store and manage PAR data collected from the individual controllers. Finally, the main controller features a custom REST API that provides secure access to all system functionalities, allowing users to manage lighting settings through the system's locally hosted web application.
Hello, I'm going over our Biosphere 2 full stack webpage. Here I am signing in with Google OAuth. We also use Arizona's NetID Plus to authenticate our users. The first page you're going to is a light status page. This shows you all connected lights to the system, as well as their color ratio and intensity. Here you're able to add in new groups and add in new lights. In our schedules page, the Biosphere 2 team is able to create 24-hour lighting schedules. Here they're able to select the color ratio and the intensity. This creates one node, and then when they create a second node, it makes a line of best fit between those 2 points. Once the schedule is made, you're able to save the schedule and execute it. Our manual control page allows you to select a certain light and manually change their color ratio and light intensity using a slider. After you click on the resume button, it takes it to its last executing point on their schedule. For the reports page, the first modal you see is the system status. The main controller's housing. You can see environment temperature, humidity, CPU temperature, and API connection. Next, you can see the par data collected by the system as a graph and also as a tabulated list. Finally, you have schedule history. This shows you all previous schedules executing on the system. Finally, for our users page, you'll be able to see all authenticated users for the system. Here, a system administrator is able to add a user and enable system notifications for them or delete users.
The Biosphere 2 ocean environment is very corrosive due to the high humidity levels and high amounts of salt fog. Salt fog is when salt particles get suspended in the air, which are generated by the salty ocean. This facilitates the need to have all of our electronics stored in waterproof and corrosion-resistant housings. Our solution to this is to use pre-built McMaster car housings made from ABS plastic. ABS plastic is non-corrosive and resilient for the ocean environment. Additionally, pre-built housings are easier for our sponsor to get than custom housings once they scale up our prototype to include 86 lights. Our main controller housing, shown here, features a custom heatsink and stainless steel wall to radiate heat to ensure our Raspberry Pi 5 does not overheat. The Raspberry Pi 5 is supported by a custom 3D printed stand with a track system that provides a secure but removable attachment method for the Raspberry Pi 5. The housing also has a desiccant packet for extra moisture absorption and custom stands for the desiccant packet, CAN bus, and has cable glands to ensure a waterproof seal around cables and wires passing through the housing. Our individual housing is a smaller pre-built McMaster car housing featuring a desiccant packet and cable glands, which as mentioned before provide a watertight seal for cables and wires passing through the housing.
So here we have our manual control page. The purpose of this page is to allow users to easily see the status of the lights and control them using a slider for speed or a text field for increased accuracy. So here we have lights 1, 2, and 3, and we're going to be doing a quick demo using this page. So first of all, light 1, we're going to be moving from blue intensity to white using the slider. As you can see here, it's changed, and now we're going to move on to light 2. We're going to be doing the reverse, moving it from white intensity to all blue intensity using the slider as well. And finally, we can show off that we can control the light intensity using the text field as well. For more accuracy, we're going to be moving from 100% light intensity to 20%, and finally to 0%, turning it off. And that's how our light control page works.
In conclusion, our user-centered design complies with all system requirements and delivers a solution that doesn't exist commercially. This system is crucial for mesocosm scale research, where consistency and precision helps researchers simulate real-world conditions as closely as possible. We want to say a big thank you to Biosphere 2 for this opportunity, and thank you for watching.